I'm really delighted to introduce Matei Zaharia. He's not a stranger to most of you, but I thought I would introduce him anyway. For those who don't know him, he was an honors student in computer science and C&O at Waterloo, graduating in 2007, and won the Governor General's Award for graduating with an incredible GPA. I can tell you that he was a student in my class, and he got 108 out of 100, which was just because he did all the extra questions, but his GPA was stratospheric, is what I will say. I had the great fortune to work with Matei when he was a URA with me for 3.5 years, starting with his 1B term. And we ended up writing a few papers together, after which he went to Berkeley. And as many of you know, he worked on Spark for his PhD, which has become a very successful open source project. He also then started Databricks, another company which is commercializing Spark. Matei has won a number of different awards, including the ACM Doctoral Dissertation Award, and that led to the publication of his first book, which is in the ACM series, and that's his PhD thesis. And subsequently, he wrote another book from O'Reilly, Learning Spark. I have yet to do that, but I plan to next year. And after his PhD and taking a break with Databricks, he went to MIT as a faculty member. He has subsequently moved to Stanford and has been there for the last year or so. And today he's going to talk about Apache Spark and Weld, which is recent work that he's done. I should mention, bears mentioning that Matei is actually not that well, so he is going to nevertheless give us a talk. I'm really thankful for this, and look forward to the talk. So let's all welcome Matei.
Okay. Okay, can you guys hear me? It's on, it should be on. Can you hear me? Okay, cool, yeah, so I apologize, but unfortunately I've got definitely some kind of nasty cold with perfect timing so that it overlaps with this talk. So, you know, I did my best using all the known methods in science to try to get better before this, but it didn't quite work. So, so I'm going to try to give the talk, and hopefully I managed to actually make it through it. So I'm going to talk basically about a line of work that's kind of been the system side of my research, starting at Berkeley and then going through to Stanford to some of the work we're doing now, which is this idea of composable parallel processing. So what's the background? In general, modern hardware platforms you work with are almost inevitably highly parallel. So things like a data center, there are thousands of servers in there. You have to figure out how to program that. But even on a single machine, if you use something like a GPU or multi-core, it's a highly parallel device. And that's because of basically the inability to speed up individual processing cores anymore, so you have to deal with this. And the downside is, of course, that they're also increasingly difficult to program. And all the tools, if you've ever tried to program either of these things, you know it's kind of a pain. It's only really for experts to work with. So in this talk, I'm going to talk about making these platforms much easier to program using essentially the main trick that we've used to make pretty much anything else easier to program, which is composability. So composability is the way that we make it easy to build software, but it's kind of taken a back seat in a lot of the parallel processing APIs. So I'll talk about what that means here and give some examples. And I'll give examples from cluster computing with Apache Spark and the evolution of APIs inside that, and also from single node systems. So just to step back, I would argue if you just ask like, hey, why are people at all productive writing software, the main way that people are productive writing it is through composition, by being able to bring together abstractions and software written by others and combine them into an application. I think that's like the whole thing when you learn to program. This is exactly what you're doing. And everyone who works on software kind of knows this. You've got, for example, Python. The reason Python is awesome is because you've got all these packages you can just import and start doing stuff. Another example is Stack Overflow. Actually, something I found out recently in Microsoft Visual Studio, there's a plugin that lets you just type in some terms and put in the top answer from Stack Overflow as well. So that's kind of how we become productive using software. But if you look at either the kind of big data, distributed computing style APIs, or like the GPU, OpenCL type things, they're not actually very good at this kind of stuff. And I'll start about talking about the big data APIs, then I'll go back to single node, massively parallel hardware. So the early big data APIs, if you look at things like MapReduce and Hadoop, they did not support efficient composition. There were kind of two problems with them. The first is that there were specialized systems for each workload you wanted to do on a distributed cluster. So if you wanted to do, well, one map operation and one reduce operation, there was MapReduce. If you wanted to do SQL queries, companies like Google and Yahoo and Facebook built separate systems to do SQL, which would solve a lot of the problems that MapReduce did, but specifically to run SQL. If you wanted to do machine learning or graph processing, there were specialized systems for those as well. So that was one reason you didn't have composability. The second reason, which is more of a technical reason, I guess more of a reason it's not efficient, is slow data sharing. So if you ever had to write an application using, say, MapReduce jobs, the only way to do data sharing was write stuff to a file. And writing stuff to a file in a distributed file system is very slow, and also you lose all kinds of type safety and stuff like that, so it's just kind of a pain to work with. And people had the spaghetti code of dozens of jobs that work together. So from early on, the Spark project aimed to address some of this. We didn't think about it too much as composability before, but we quickly realized that's kind of the key aspect. So Spark provided two things. General engine that supports a variety of these applications that we had, and also composable APIs, these functional APIs, where everything is just kind of a function call, and you can combine them, chain them together, and pass these distributed data sets between them very easily, regardless of which libraries you use. So if you've seen it before, the Spark API basically lets you build these distributed collections called resilient distributed data sets using transformations, where you typically pass in functions to execute on all the data items. And they're type safe, and no matter how you build them, you can always do the next sequence of operations on them. So you can split up the code into libraries and things like that, and build up an RDD out of many little pieces and get it to work. And then it also does a few things to make the composition efficient. So it actually pipelines the execution across these things, and it does in-memory data sharing via Java objects, so that you can quickly pass data between different libraries and functions that you've combined in your application. And this is really the main thing happening in the scheduler, but it's enough that, in reality, people build lots of libraries on top of Spark that you can easily compose and still get an efficient program. Okay, so how well did this thing work? Users actually really like this unification part, and the functional API as a way to do composition did create some challenges. It's not perfect. So these are actually things we're addressing in newer Spark APIs over the past couple of years. So first, let's just talk about libraries. The bulk of the project ended up actually being libraries. So this idea of like, hey, let's have a small core engine that enables composition, and let's have libraries, did work out pretty well. And in reality, people use a lot of these together. So most applications use at least two of these libraries, and sometimes even more, to build something. So users really appreciate that aspect of the Spark design. And the cool thing in Spark is you can just import these libraries and chain them together and compose them. So for example, in this one here, we're using the Spark SQL library to select some data. Then we're using the machine learning library to train the model. Then we're applying that model to a stream of tweets. And we don't need to do anything special for that to be efficient. So for example, this stuff with the k-means actually will get pipelined and co-located with the SQL queries based on data placement and so on, and you'll actually get a pretty efficient execution. And compared to the separate frameworks people used to have on clusters, it's a lot less reading and writing data to a file system, and basically it's a lot more opportunity to make this efficient and fast as well, not just easy to use. Okay. So that's kind of the core Spark API, the functional API. Even though it's really nice and it's like easy to combine these things, though, there were some challenges. And I'll talk about these next, and then I'll talk about how this kind of thing is evolving, because we, once we realized that this was like the most important thing to try to support well in Spark, we wanted to create a better version of it. So the functional API looks really high level, but unfortunately it hides a lot of the semantics of the computation from the engine. And that makes it hard to actually do the most interesting kind of cross-library and cross-function optimizations. So for example, the functions you pass in are just arbitrary Java code, and the data stored in it is arbitrary Java objects. So when users mix the API in certain ways, you get inefficiency, even though maybe intuitively, we think that we could actually get more efficient execution. I'll give you a small example of something that people do. So one example is when people try to do word count in Spark, you can do it using a map, turn everything into word, comma, you've got some words, turn them into key value pairs with word, comma, 1. And then you can do a group by key, and then you can take each group and compute the sum and get the sum of that word count. Now, does anyone know what's inefficient about this? Yeah, group by. Why is it bad? It shuffles everything. Yeah, but it's actually worse than that. So one issue with this is group by key actually is supposed to give you a sequence of integers for each key. That's the signature of it. So group by key is you take an RDD of these key value pairs, and it gives you one with keys and then a sequence of integers as the value. So not only does it have to move all the ones around on the network, but it can't pre-aggregate them. It has to create this giant list of ones for you to look at. And that's because this is just the type signature of it, and Spark is just based on these Java classes and Java data types. So that's what we have to return. We can't return something else. Even though later on, if we were to look, we would see, oh, you're just adding them all up. Maybe we could have grouped up the words locally on each machine first or something like that. So just because of the way we wrote the API, there are these limitations. And users still have to know about some of this stuff. And this example maybe seems kind of stupid because there's just one user here who wrote all this code. So like maybe it's their problem that they did this. But remember that we talked about software composition. So what could really be happening is there's one library someone imports that does this, the first two lines, and then there's another library or custom code they write that does the last line. So then the people writing the first library are just trying to give you these groups. That's what the library is supposed to give you, and that's awesome. But then in the way you use the result of that, you actually don't need the full group, you just need the sum. So this is the kind of thing that we want to enable, is people should write these things independently and we still get efficient execution. And that happens a lot in large code bases too, where different people wrote different pieces of the code, and now in Spark they need to worry about like, hey, what exactly am I doing with this data? How am I combining it, and so on. Okay, cool. So this is, this is the problem. Okay, So next I'll talk about basically the work to address this in the Spark project, which is work that started basically around 2015, or maybe, yeah, around what are called structured APIs in Spark. And a lot of these became kind of stable and sort of the default for many things in Spark 2.0, which was about a year ago. So the structured APIs are these new APIs based on structured data. What do I mean by structured data? Well, at least in Spark here, it means this kind of limited table-like data model, kind of like a database table, although it has a few more data types than that. But it's not arbitrary sort of Java objects. It's actually this small data model that we can understand. And there are 3 APIs that build on this: Spark SQL, which answers SQL queries, DataFrames, and datasets, which are for developers. And they support similar optimizations to kind of relational databases, in particular because they know the structure of the data and they also know the structure of the operations you're doing it a bit better. They can solve problems like the one that I showed before. And at the same time, they have some of this language integration and programmability that you had with integrating this stuff into a high-level, like full-powered programming language. Okay, so how do these things work? So basically, no matter which of the APIs you're using, it produces a logical query plan underneath, which is a lot like your database logical plan. And then this gets optimized into a physical plan. And then there's a code generator that actually produces a program using RDD. So it just runs on the same engine we had before. Didn't have to change anything. And then the final bit that's actually pretty powerful is something called the data source API, which also lets you support different data sources and even push part of the query into those. I won't talk about it too much here. So just as an example of how this looks, I'll show DataFrames, which is the most popular one. So DataFrames hold rows with a known schema and offer relational operations on them through a DSL. So for example, here's how you might use Spark DataFrames in Python. You could start with a SQL query, and then you've got this DSL that lets you do different transformations on it. So note that the thing in here, this weird like user state equals California, this is actually kind of an abstract syntax tree or a little expression in this DSL. If you're familiar with the Pandas library in Python, this is what this is modeled after. So it's not an arbitrary thing. This is actually a super widely used data science library. So the nice thing about this compared to before is it's not just a blob of code. It's actually this expression tree that we get to see, and then we can do stuff like analyze it and say, oh, you only need the state field or something like that. We don't need all the other ones. Okay? And then you can do these standard things. If you want to do group by, for example, this is how it will work. So in this case, you actually see that you're grouping and aggregating right after. And then if you want, you can also fall back to passing in arbitrary functions. So here I'm just passing in an arbitrary Python function. So that's kind of what the API looks like. Very similar at a really high level, but much of the stuff you can do through this DSL or domain-specific language, and you don't have to do through passing functions all the time. Why did we choose to build DataFrames? These things are actually kind of exploding in popularity in data science, especially single-node processing tools. So they're very popular in R as well as Python. And kind of the crazy thing about DataFrames is inside they're just doing relational operations on a table, similar to a database. But no one had tried to have a query optimizer for them or to make it a declarative API. So in Spark, we actually made them a declarative API. We made them lazily evaluated, and we added an optimizer. And we can get essentially the same syntax as the Python and R data frames and get really nice optimizations too. And compared to just writing giant blobs of SQL everywhere, hopefully it goes without saying, but it's pretty nice to be able to just integrate these into a program, maybe break your program into functions and build up one of these expressions in that way. So that's why people like using this kind of stuff in Python. Okay. So underneath these APIs, we can do a lot of stuff that we couldn't do in the original Spark API. So we can represent data in a nicer way, like a columnar format. We can optimize across operators, push things like filters and joins around, or fix the problem I showed earlier with the group by. And we can also do runtime code generation, generate some Java code to execute something from this kind of SQL plan that we got before. And the end result is that these things perform really well. They actually perform better than using the RDD API in many cases because they fuse together lots of operations and they specialize them for your data types. And they also perform consistently in all the languages you're using, whereas the stuff based on user-defined functions, it's slower, for example, in Python than in Scala. And so that's kind of DataFrames. And DataFrames are actually the foundation of a lot of other new stuff in Spark, which I won't have time to talk about, but which is actually like pretty cool. So for instance, high-level machine learning API, graph API, streaming APIs that use these, and all of these benefit from these like much richer optimizations across operators that you have. Okay, cool. And then the last bit I'll talk about is some newer research, which is this system called Weld that I'm developing at Stanford. So Weld is targeting more of single machine performance, although of course you can use it in a distributed system too. Basically the idea is that with continued changes in hardware, your machine is essentially a distributed system, and memory is often the bottleneck for a lot of applications. Like I talked about how sharing stuff through files is slow in the original kind of big data frameworks. Sharing stuff through memory can also kind of dominate the cost for data-intensive applications on a single machine. And what this means is that the traditional interface for composing libraries in this kind of single machine setting is increasingly inefficient. So what's the traditional way we've been doing this stuff? Well, it's basically function calls. You write a function call where basically you can pass it some arguments through registers and things, but more likely for any big arguments, they're sitting somewhere in memory. And you pass it a pointer to those, and it gets to run, and then it outputs stuff to a buffer in memory as well. This is the interface we've been using for structuring kind of our single machine libraries in the past. But if you've got data-intensive functions without too much computation per byte of data, this data movement can really kind of dominate. So here's an example of like 3 functions in Python for a simple pipeline. So basically, we're going to start with a string in memory, parse it as a CSV file, comma-separated values, then drop the not available values, and finally compute a mean. So in this case, we basically read and write through this big data set about 5 times as we scan through it to read it and write it, even though we could be doing stuff on each record in a pipeline fashion and probably finish much faster. And this kind of data movement back and forth can really slow things down. So we benchmark some idiomatic code in widely used libraries for single machine stuff. All of these have optimized individual operators. So the operators are all written in C++, they're very fast. But just if you combine dozens of these in a program, you get slowdowns of 5 to 30x compared to just like running a handwritten piece of code. Okay, so that's this part. So how are we solving this in Weld? Sorry. Our solution is basically to design kind of a language runtime. Think about something like the JVM, but for this kind of embarrassingly data parallel code. Sorry. So the idea is that your computation, all the data-intensive parts, will map down into this intermediate language. Think about this like your bytecode. And then we'll optimize this stuff together and run it on diverse platforms, CPU, GPU, and so on. So there's kind of two pieces. So first is the runtime API. This is a little bit like an OpenCL or CUDA type API, except that it's lazily evaluated. So basically, libraries can register data that they want to compute, maybe taking as input previous ones, but they just register a function or some code. And the runtime doesn't have to immediately evaluate it. It can wait to see a bunch of these, then combine them and optimize across the code and then actually compute something. So it's kind of interesting because basically as a user, it's not that different from using something like CUDA or OpenCL, but it actually creates this room for more efficient composition. Whereas with those APIs, you have to tell it from the beginning, here's exactly the chunk of code I need, and then it's going to run exactly that code. So that's kind of this part. Very similar to Spark as well, lazily evaluated pieces of work. And then the second part of Weld is the IR. This is this kind of very simple functional intermediate representation based on something called monad comprehensions. And this has basically two pieces. It's got these parallel loops that let you iterate over a data set, and it's got something called builders, which are these declarative objects for producing results. Things like appending items to a list or computing computing a sum. So these tell you what result you want to get, but they don't tell you how to implement it on a specific piece of hardware. So we can actually implement it very differently, like say on a GPU versus a multi-core. And this is really meant to be kind of a generalization of the type of IRs we tried in Spark, for example. So it can support relational algebra, linear algebra, these functional APIs, and also composition and nesting, unlike, for example, the stuff in Spark, which doesn't let you have nested parallelism. So I'll give a couple of examples. In these examples, I'm going to build some functional operators using builders. So first one, I'm going to do map. Basically, to implement map, I've got some data and a function. The way I can do it is I can create this vector builder, and then for each item x in the data, merge f of x into the builder, and then call result on it. So the way it works is this is a data parallel loop. All the things happen. Basically, all the loops in Weld can happen in parallel, but they are associative. So the things will get merged in the specific order that they came in from there. And in parallel, we'll be adding these items into a new vector. And then this result finalizes it and actually gives us back a result. As another example, let's say we want to implement reduce using loops and builders. It's really similar. So basically, in this case, the builder, instead of being this vec builder that produces a list, it's this merger that takes a 0 and a function for merging two items. And then for each item, we just merge it in there. Again, this is an associative thing, so it's guaranteed to keep this order, basically. And then we call the result. So what's cool about this IR? Well, the cool thing is it's really easy to express optimized versions of the code where you do things like fusion or otherwise try to reduce data movement. So for example, say we had both a map and a reduce over the same input data. That would become a single loop that updates two builders, the vec builder and the merger. And this is the kind of thing where if we just used, for example, relational algebra as our intermediate representation, it wouldn't be very easy to express this. There isn't really an operator in there that's doing both mapping and reducing kind of in the same pass. But here we have this really tiny language that can do both. All right. So hopefully this gives you a bit of an idea of how that works.
How do you get the X that you merge into build 2? How do you get that to be the result of the first build?
Oh, these aren't chained together. These are two independent results.
Oh.
Yeah. If you did want to fuse them that way, though, like if this was reduce of squares instead of reduce of data, then you would just have to inline this like somehow. Actually, Weld will do that as well, but yeah. Yep. Cool. Okay, so how does it work? So does it actually help with kind of this single node massively parallel performance? So it turns out that it can actually help quite a bit. We tried integrating Weld into a bunch of frameworks. And basically, in all of these, Weld makes a difference of about, I don't know, 4 to 5 times compared to running the system by itself. And that's because in these frameworks, even though you've got many individual operators that are each implemented in C, they're very optimized and so on, in reality, no user program just uses one operator. They use dozens of operators. And so the data movement across them can really dominate. And you can actually make it, make things faster by doing this. And then it also helps with cross-library optimization if you combine many of these frameworks. So imagine even if NumPy and Pandas or TensorFlow or whatever each build their own compiler, real applications will combine many libraries. So this is showing here a simple workload using Pandas and NumPy. It's like a data science tutorial workload. And basically, this is Weld with no cross-library optimization. It's about 9 times faster. This is with cross-library optimization. It's about 30 times faster. And then the other thing, a lot of these libraries are single-threaded, but the operations they do are kind of embarrassingly data parallel. So it's kind of silly that they don't run in parallel. And with Weld, if you just turn on a multi-core backend, they will do that. So it's also a nice way to get multi-core parallelism out of your application. Cool. And then the one final thing I wanted to show here is comparison with specialized systems. So we also compared with systems that implement the compiler either for SQL databases or that hand implemented a specific piece of code. Like, for example, this TensorFlow workload, the TensorFlow developers implemented it in a single operator because it's so slow to express it idiomatically as many different operators. And Weld also performs pretty comparably with those. Basically, on data-intensive stuff, it's often competitive or within 2x of this kind of hand-optimized stuff. So it's pretty cool to see that even with this really small and general intermediate representation, you can get pretty efficient code. It's mostly because data movement is the bulk of the cost, and that's the thing that we try to minimize. Cool. Okay, so hopefully this gives you an idea. There's lots more happening in Weld, including pushing some of the query into I/O, optimizer and new hardware backends, and it is open source if you want to check it out on the Weld website. So this kind of ends what I wanted to talk about. Basically, to summarize, the way we compose software will have to change in order to effectively use modern hardware. Data movement is really expensive, and compared to many of the other things in current applications, and that means rethinking the interfaces between them. And I think because of these examples that we have so far, that if we do this well, we can actually open up this kind of highly performant hardware or data center scale computing to a lot more people. So we'll be able to actually have high-level composable libraries for doing this stuff, and this is what we're trying to do with the Spark APIs and with Weld. Okay, thanks. Happy to answer a couple of questions.
So there's a lot of work in CodeChat in DBMS backend, and it's also an intermediate representation game, and they do all of these cross-operator optimizations. Do you think Weld can be, like, by sitting under this, is there will be benefit in these much larger scale? Like, it's very clear when it's data science and I'm putting things together, and I don't have a backbone that does any optimization.
Yeah. That's a good question. Yeah, so you're talking about people who write a compiler from scratch, like a SQL to whatever compiler for their database. So actually, having worked on one of those in Spark, the Spark SQL to Java bytecode compiler, it's super painful to write that kind of thing. So I actually think Weld makes it easier because, and actually that's what we found in, for example, in the ports that we did of Spark SQL over it. So normally if you're writing your compiler from scratch, you have to look at all the operators and generate this like really nice loop that does all of those things together. In Weld, you can instead write these like separate steps. For each operator, you don't need to look up and down the chain at all. And then Weld will do the fusion across them in some sensible way. So you might lose like a little bit of performance maybe compared to hand controlling everything, but the software engineering benefits are pretty big. So we're actually trying to do kind of a full implementation of one of these things in Weld. Yeah. Mm-hmm.
So I'm looking at this, all the interesting work you're doing with this Weld runtime, and I'm wondering whether you have a sense of how much of the optimization work that you're doing here is getting around sort of complexities that are caused by the Spark API itself, the sort of functional, transformational notion of the Spark API, right, that you have to work around. So I guess the bigger question is, you know, do you still feel that the Spark API is the right way for people to write these kinds of programs?
So I think a lot of this isn't actually motivated by Spark, but rather by the single node libraries like Pandas and NumPy that people are running today. So I think it's just inherent in the way people write stuff. Like even if you're using BLAS, for example, in C, you'll run into this problem. So it's not really based on that. It is true that this makes it a little more complicated to program stuff because you need to make stuff be lazily evaluated or deferred somehow so you can see more of them. But I don't think it's specifically from that. I think it's just you want to write code by calling a few functions. Yeah. Okay.
I'm just curious if
Yep.
the similar notion to database integrity constraints has impinged at all, or is that something on the radar scope with this well? Sorry? Oh. Did you hear the question?
Kind of, yeah, integrity constraints. Yeah, I don't think we've looked at it too much, but I think it could be interesting to basically you're asking like how much could you know about the data in advance. Yeah, we haven't done a ton with that yet.
So maybe I'll ask a question because I have a dumb question, I guess. What if you took awk as your front end? After all, what you're doing is what awk does in every loop, right? So why not just use awk and parallelize the back end?
Oh, you mean, could you make that a front end? Yeah, I think that's not a bad idea, actually. That would be pretty interesting. Yeah.
Okay. All right, because I can program in awk and not in Spark. Any other questions? Yes. Okay. Maybe I can get David.
So can you do anything for workloads that are not embarrassingly data parallel? As a concrete example, compilers? Compilers?
So we haven't tried to. We only tried to do the embarrassingly parallel ones. The thing is, basically we tried to write like kind of the simplest possible, like essentially functional language that we can do anything in parallel for. So we tried to keep it very bare bones so far. Yeah. But it would be great to look at this in other places. We are actually, one cool thing we're doing recently is this thing, which is actually, it turns out like parsing data is very time consuming in a lot of big data workloads, or even parsing like things you read off a wire or something. So we're saying like, and normally parsers, they are this kind of more sequential code that's producing lots of records, and we're saying, hey, how can we pull out only the pieces we need? So, yeah.
Am I allowed? So I guess my question is, supposing I'm a real dummy and I write these functions that have some dependencies between them, can I you know, and what I want to do is get you to waste a whole bunch of time trying to figure out what's wrong with your system. So I run it with all your optimizations. It gets a different result than if I'm running it in standard TensorFlow or something or other. I mean, what's your defense against me?
Yeah, so I think basically right now I think we're relying on the people who write the functions in Weld to not create these side effects. Actually, in the language itself, you can't really create side effects in any way except by calling a C function, like an external function. But the idea is like if you're the TensorFlow developers, for example, you can implement each of your operators, or like say your 10 most popular ones in Weld and enable optimization across those. But it's not that ordinary users will use this. Ordinary users will just use the normal API.
Any other questions? Okay, great. Well, let's thank Matei again.
Thanks.